In this lecture, we will work out an example in finding the polynomial of smallest degree that goes through a given set of points. In the graph shown below, we have 5 points, p sub 0 through p sub 4. For any given set of points that goes all the way through p sub n, there is a unique polynomial of smallest degree that contains all the given points. That polynomial is called the Lagrange polynomial and can be written in the following form. In this expression, a sub 0, a sub 1, all the way to a sub n are unknowns. Instead of plugging in the coordinates of the different points into the polynomial equation, and then solving the resulting system of equations, we will use a formula for the Lagrange polynomial. For p sub 0 through p sub n, using fractions of polynomials, the Lagrange polynomial can be written in the following way. The viewer might be able to see what the pattern is for each of the fractions. But instead of discussing the pattern for each of the fractions, we will go through an example and then use the example to talk about the pattern for the individual fractions. For the example, we will use n equals 4 as is shown on the graph. The Lagrange polynomial will have 5 terms, 1 for each point. And here are the coordinates of the points that we will use. Before we plug in the different coordinates of our points into the formula, we take note of the pattern behind each fraction. Let us take a look at the first fraction. This fraction is for the point p sub 0. Note the lead factor y sub 0, which is f of x sub 0. And in this product of linear polynomials, x minus x sub 0 is missing. In the denominator, observe that x sub 0 leads off each individual linear factor. And from x sub 0, we subtract x sub 1, x sub 2, x sub 3, and x sub 4. In short, x sub 0 minus x sub 0 is missing. X sub 0 minus x sub 0 has to be missing from the denominator, otherwise we end up dividing by 0. Well, let's take a look at the second fraction, the one for p sub 1. Observe that the lead off factor is y sub 1 or f of x sub 1. In this product of linear factors, x minus x sub 1 is missing. In the denominator, x sub 1 leads off each individual linear factor. And for each factor, from x1, we subtract x sub 0, x sub 2, x sub 3, and x sub 4. In short, x sub 1 minus x sub 1 is missing in the denominator. So let's start plugging in values into the different fractions, starting with the first fraction. We lead off with y sub 0, the y coordinate of p sub 0, and so we have 3.7. The first factor in the numerator is x minus x sub 1, or x minus 2.03. This is followed by x minus x sub 2, or x minus 3.326. Then we have x minus x sub 3, or x minus 4.191. And finally, it's x minus x sub 4, or x minus 4.715. Each factor in the denominator starts out with x sub 0. The first factor in the denominator is x sub 0 minus x sub 1, or 0.55 minus 2.03. The second factor is x sub 0 minus x sub 2, or 0.55 minus 3.326. Next is 0.55 minus x sub 3, or 0.55 minus 4.191. And last we have 0.55 minus 4.715. Now let us try it out with the second fraction. Starting off with y sub 1, which in this case is 3.421. The first factor in the numerator is x minus x sub 0, or x minus 0.55. We skip x minus x sub 1, and so the next factor is x minus x sub 2, or x minus 3.326. Then it's x minus x sub 3, or x minus 4.191. The last factor, x minus x sub 4, or x minus 4.715. In the denominator, we're subtracting everything else from x sub 1. The first factor is x sub 1 minus x sub 0, or 2.03 minus 0.55. We skip x1 minus x1, and so it's x1 minus x2, or 2.03 minus 3.326. Then it's x1 minus x3, or 2.03 minus 4.191. And the last factor is x1 minus x sub 4, or 2.03 minus 4.715. We leave it as an exercise for the viewer to check that the last three fractions to complete the Lagrange polynomial are given by these three fractions. And simplifying, this is what we get for the polynomial.